Um, Hello, this is William Coleman, and I am presenting my term paper project. Uh, the topic is mitigating firmware tampering and side channel attacks in IoT devices. It's a literature review. I'm here at FIU. I'm an undergraduate senior. I'm studying for my bachelor's in IoT. This topic intrigued me because of a project that I was doing with MITRE. They have a competition called Embedded Capture the Flag, and I was a part of it this year. I was able to like lead the team for it. It didn't go so well, like when it comes to attacking, because it's split. Like you defend they have a system that they want you to make. You add security to it, and then you would later go into an attack phase where you attack other schools like Carnegie Mellon, Purdue, just like there's over like 100 schools that are part of it, and the defense went well. Kind not really. Well, the team like stuff was hectic, but we got something together. The attacking was more of like I didn't know how to do that. I This topic was meant to kind of mitigate that. The title name, because like firmware stuff and like side channel attacks. I learned a lot reading into this, and this was kind of cool. So first we can start with introduction. Firstly, it's a problem statement. Is how can we mitigate firmware tampering and side channel attacks? Um, One thing like I want to talk about before we like get into much of anything is that there's like 18.8 billion IoT devices that are currently connected. Last time it was audited in 2023, and that's a lot of them. IoT has been on the rise like since the 2000s, my bad, for the last 2 decades. And manufacturers and companies, they are churning out the number of the devices, but they're not making them in the most secure way possible. It costs more for them to add um, placeholders or capabilities on the device for security, and it doesn't raise how much they get in the actual consumer market. So they default to not adding any security capabilities, which is not a fun thing to do. Because then someone buys. I wouldn't. I'm not gonna say specifically that they have the issue, but someone buys like a Ring camera and they buy like an Amazon Alexa, and then they have it listening into the conversations that they're having in the house. Someone penetrates into the device, they're listening in, then the person knows their when the family or maybe it's one person when they're gonna leave, and the person can come back and rob the place. You know, it's a bad thing when you don't think about security. It especially when you're selling to the public, it's not a good plan. So my paper, this is I'm not diving into that, but one of the papers that I read was about like the landscape of IoT security, and they dove into that a lot, and that was kind of cool to read about. And one of the things that they also brought up was the IoT like architecture. You have to There's different ways of setting up an IoT system. Uh, the beginning, like the first or most commonly used, is this three-layer architecture, which is like the example I think that most would probably give. It's starts at the perception layer. This is like the sensing and physical layer. You might see a different website or page use that wording instead. This holds all of the embedded devices, the sensors that are connected to those devices. This is where edge computing would be happening, if I'm not mistaken, as well. But yeah, I mean, that's where all the information gathered from the real world, and that goes into the network layer, which connects the perception and application layer. All the data and information that is received on the perception layer is sent to the application layer, and the application layer, um, that's where all like the what's it called? The computing happens at. It's like if you're in a business meeting and you're doing IoT, You might, I don't know what company, you might work for a water company. Maybe guys have devices out checking water level and the acidity of it and the different composition of the water. Maybe researching algae. Um, but once you get to the application layer, that's where you're gathering all the information together. Maybe you're putting it into nice charts. Maybe you're using it for a separate program or application, which is why it's called the application layer. Like you can have an app that reads those things, and it's that app is continuously on a network with those sensors. So it's from your phone, you're able to read those. You're able to see the readings. Well, yeah. But there's also 4 layer and a 5 layer. Like a 4 layer adds uh I forget what the layer's called. But the fifth one, like you can add like a gateway layer, do this and do that. I forgot what the rest of them are called. But we can go on to this is the chart showing off the like attacks, or rather like with that architecture of the perception network and application layer, these are like the threats to each layer, and a few attacks and or like concerns per layer. And so like for the perception layer, you have the physical device threats because like those are the embedded devices, the sensors. One of the concerns are resource constraints, and this is actually where we have identity loss, destruction of nodes, mainly middle attacks, and this is our tampering or physical damage. This is the firmware tampering that we're going to get into later. Side channel attacks happen at the network layer, where there is network communication threats like controllability. And the concerns are controllability, manageability, and heterogeneity and protocols. Heterogeneity because not all devices are built the same, which is something I should have mentioned earlier. All devices are built by different manufacturers. There's so many different manufacturers, and they are then, depending on the company, they'll be using different um, communication protocols, and a few things need to be able to communicate together. And so there's always like a period of time where things are trying to merge and it might not work. In those cases, a device is terminated off of like a system. But that's an issue that is normally addressed. Then in the application layer, you have information data threats. This is where you have the CIA, which is confidentiality, integrity, and availability. Um, Things to consider about to worry about in there are replay attacks, data modification, impersonation, and buffer overflow. So from here on, we're going to be talking about the attacks that we're actually dealing with. Um, firmware tampering. This is firmware. We'll talk about it for a second. It's the soul of smart devices. It is the low-level software. It's commonly used or made or coded using the C programming language. It manages the device's hardware and offers a user interface for communication. Normally, you would code the device. You know, if it's in C, you're adding buffers and this information here and there. The buffers would be a certain size, and it'd be the size of the information that you would be tending to send to the device. Um, you have different operations happen on a device. If it's made with security or you have some software security on it, then the operations would happen and everything is coded in there, is built into a binary image, and that binary image is the firmware like image or similar to that. Um, Firmware updates are necessary to fix bugs and add new features to IoT devices. Firmware is initially put onto the device, and then afterwards you can do some more updating afterwards. That's what the point of the updates are for. It involves transferring an updated firmware binary to the IoT device. The implementation of this updating depends on the type of communication the IoT device uses. For example, HTTPS and TCP. Firmware tampering attacks, they aim to inject malware into the target embedded device, and they can be carried out in either a standalone attack or a secondary attack following initial exploitation using traditional attack vectors. Um, for this, we're going to be focusing on the standalone firmware tampering, which it manipulates firmware updates instead of using of exploiting flaws in the victim software like other attacks tend to do. Um, Something to note is that like insecure firmware updates are the bread and butter or like the target most of the times for firmware tampering. Um, if you don't have the proper authentication steps when updating like firmware to the device, then someone can modify it, try to update to the device, and if you don't have the authentication, then it will just work. And so that kind of stuff is not good. Next, we talk about the side channel attacks. There's two types. We have passive and active, and side channel attacks. They are the most concerning attacks during data exchange. So, like for the competition I was talking about, we were doing a satellite TV system and we were sending frames from like uplink went to satellite and the satellite went to our computer. We had a decoder connected to our computer and it sent frames to it, um, essentially directly from the satellite. So we encrypt the data and then we decrypt it. And side channel attacks are basically when encryption and decryption happens. It was something that was discovered like more recently. Is that when encryption happens? Or maybe not like more recent, like not like the last 5 years, but like the last like 10 years. Um, when an encryption operation happens, there is some like extra data that's leaked when the operation occurs, and that's considered side channel data. And so side channel attacks are attacks um, based on that information that's leaked. And normally, these side channel attacks are trying to retrieve keys that are in the device. Those keys are normally used for like cryptographic operations, such as encryption and decryption. It can also be used for authentication, like with the HMAC, hash-based message authentication code. Um, and I'm actually going to show you a visual of what this kind of looks like. You have a sender and you have a receiver, and they're sending messages in between. This is like the key, so key A and key B. When this like stuff happens, you have a message going in, and this is someone analyzing it, the kind of message transfer. It goes through, comes out. Things that end up like leaking are frequency, a fault, power, sound, heat, and light. And I guess as well as the message itself, but these few things are the main attraction, especially power analysis and sound as well. Um, these attacks, by the way, societal attacks can be categorized into active and passive. When I'm talking, when this presentation is happening, we're mostly referring to active attacks instead of passive ones. The passive attacks are like simple. They can be they are two types of passive side channel attacks. It is a simple attack and a differential attack. We're discussing active side channel attacks, and those are also known as tamper attacks since you're using the side channel information in order to tamper with the device. They have a lot of different implementations, those tamper attacks. They use all the information that leaks out of this encryption operation, and they turn into attacks that are like fit the name of the information that tends to leak out. You have more traditionally speaking, the attacks that most people do. You have timing attack, fault analysis attack, power analysis, and electromagnetic attack. Those are the ones that are mostly used. But more recently, there are some other attacks, such as frequency-based attacks, acoustic attacks, cache-based attacks, error message attacks, visible light attacks, and scan-based attacks as well as online application like leakage. And very amazingly, these can actually be combined together to make like a new attack. It's it's a whole bunch of information. Some attackers have found a way to use it, and some prefer to use it one way. But if someone really wanted to, I mean, you could do the works. Let us speak now about mitigating these two attacks. Um, First up is firmware security. Firmware can be up protected in a number of ways. You have hardware-based solutions. There's firmware level solutions, system level ones, application level ones. Um, I don't really get into the details of these, like the different ways of the levels of it. I didn't have the chance to do that. Instead, I want to give you the best practices of securing firmware. You start off with one, secure firmware updates, where you should have like extra steps for verifying firmware. Use communication protocols, secure ones such as HTTPS. Make sure to have what I was talking about, the verification or authentication. Use digital signature verification for the images, and this subsequently ensures that the correct it ensures the correctness of the sources that you're getting the firmware updates from, and making sure that the firmware has not been tampered with. Then you have secure communication. You should I mentioned it earlier, but the device should be using a secure communication protocol such as HTTPS, TLS, the transport layer. Um, I forgot what that stands for, and SSH. And those things also, the secure communication will also protect you from man-in-the-middle attacks and eavesdropping. You can also have strong, unique passwords, strong authentication, input validation, logging and monitoring of all like the events that happen on the device. Uh, Not logs that will stay there for a long time, but ones that will periodically be deleted. And then finally, you also have a secure boots, which is the mechanism that prevents anyone from having the capability of tampering with device firmware and make sure that only official firmware can be executed on it. These few things and the passwords as well. If a user is using the device, um, have them switch through their passwords and also have a unique password. It's like when you make an account and they ask you for a 15 letter, 15 character password, and you need to add like an exclamation point. But the idea is that you'd be also switching it every once in a while. Some colleges makes you do that, so the same thing applies for firmware on your embedded device. And there's actually a product that I found while researching called Secure Elements. Maybe not a product, because there was another paper that I read that mentioned Secure Elements. So I'm thinking that the timing is that one paper. So in 2019 is when the technology, or when that paper wrote about the technology called Secure Elements. It's able to execute cryptographic operations and hardware, and it allows for fast and energy efficient execution of cryptographic algorithms. And also, it provides tamper proof memory for secure storage of cryptographic material, such as like keys and all the other messages that you're encrypting in the first place. It allows the leaf node to provide a high security level and to be an authentic and secure member of an IT infrastructure. I feel like that last point wasn't needed, but um, yeah, I mean that's basically it for this. We go over next into side channel attack countermeasures. So I'm going to use the same sort of method of doing this. We have the best methods first, or the best practices. We go into power consumption balancing. It's a technique that ensures cryptographic operations consume uniform power, regardless of the data being processed. It prevents attackers from distinguishing between operations based on power analysis. Implementations typically use constant time algorithms and balanced logic gates that mask the relationship between power usage and sensitive operations. You could even have a constant time algorithm is good, and that also prevents the timing attack specifically. One good thing for the power consumption, like instead of trying to balance it, you could also do a noise, which is something mentioned here. Yeah, so I mean it. The noise thing I'm talking about, it involves deliberately introducing random fluctuations into power consumption or electromagnetic emissions, and it masks actual patterns. Random number generators create unpredictable noise that make it difficult for attackers to isolate meaningful signals from background interference. So the idea is that like the operations that you're having on the device normally in its normal operation, um, there's highs and lows to the in like the power, like the amount of voltage that is going through the device. So attackers are able to read that and they're like, "Ooh, something's happening here," and so they go there and they're able to pinpoint when and where to start attacking. And the noise makes it, if not more balanced, then like it it plays around with it, um, with where the power's at, and basically not doesn't like fully shield attackers from attacking that way using like power information, but it is a good addition. You could also reduce the size of the signal by minimizing electromagnetic or power emissions during cryptographic operations. Um, and so this approach reduces the quality of signals attackers can capture. Techniques include low power circuit designs, smaller voltage swings, and optimized algorithms that minimize information leakage. And finally, you have shielding. A physical defensive strategy. It uses specialized materials, such as like Faraday cages, metal enclosures, or electromagnetic absorbing coatings to prevent electromagnetic emissions from reaching potential attackers, monitoring equipment. That's more of a physical defense. Like if you had your device somewhere, maybe um, if it's in a little box, you could you're protecting the box in a box. Rain is being shielded. Idea is you would coat the inside of the box with this stuff, the electromagnetic absorbing like coatings, metal enclosures. So you could just be the metal box. But the idea is that it wouldn't that the attackers wouldn't be able to use the electromagnetic um, like waves. Are they waves? Like what's being leaked from the device. There was also a product that I found for this for countering mitigating side channel attacks, and that's this thing that was at least the source that I found, they wrote about it in 2020, and it's this thing called Fisher. It's a defense mechanism against timing-based side channel attacks, specifically on the IoT network traffic. Fisher prevents the attack by identifying and hiding timing leakages, improving user privacy. Yeah, Fisher has two features. So it has a vulnerability test, and it also has an what's it called? Like a like defining rules. So like the first thing, uh, the vulnerability test. Okay, my bad. It has two things: a vulnerability test and privacy protection. The first, the vulnerability test, it collects IoT network traffic and it extracts timestamps related to the request and response messages exchanged with the gateway. The feature computes statistical measures from the collected network traffic to identify timing-based leakages. And then the privacy protection. It allows you to define rules for IoT devices to hide their behavior and possible leaks through two methods. One, inserting delays, and two, generating fake packets. to force devices acting similarly into the same time instance. It prevents attackers from analyzing the device's operating times. So this is like a actual product that does these two things. You have the inserting delays and then making sure that no packets are lagging behind time. And yeah, I mean that's Fisher. So for side channel attacks, if you wanted the product, check out Fisher. It's all caps, Fishemer. I didn't research it separately, but I did read the paper that was about it. And so I'm assuming that it is still in operation and that you would still be able to purchase it and or use it, which is that'd be kind of cool. Um, and then you also have the secure elements for the firmware attacks or for firmware security, preventing the firmware tampering. But that is all. This was a long presentation, but I hope you have learned something from what I have said. This paper was fun to write, and thank you for listening.